For quite a while, people have envisioned what life might be like in other universes. As a result of the James Webb Space Telescope, the most shocking telescope in existence, that question can at last be analyzed. While observing the nearest star system to us, Proxima Centauri, which is just 4 light-years away, researchers have noticed several remarkable idiosyncrasies from one of the planets in the system, Proxima B. These peculiarities, called counterfeit lights, have bewildered the best personalities in the area of science. In any case, what are they? Do these lights propose the presence of intelligent life? Join us as we inspect the James Webb Space Telescope's upsetting discovery of city lights that could change everything. The principal life that we are currently aware of is on Earth. Starting from the start of human advancement, people have questioned whether there is life somewhere else in the universe. To complete such an interstellar hunt, American cosmologists Jill Tarter and Tom Pearson launched the search for extraterrestrial intelligence, SETI project in 1984. The ultimate goal was to gather spaceborne radio transmissions. Radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the extraordinary Allen Telescope Array in the California lower region mountains. Anyway, before 30 years ago, no obvious extraterrestrial signals had been found. Following that, the James Webb Space Telescope's successful launch assisted the journey by enabling the observation of a level of unnoticeable planets circling faraway stars. As the largest telescope on the planet, drifting around 1 million miles from Earth and equipped with highly sensitive instruments, it has the potential to reveal giant discoveries. Quite a while ago, there were no known planets outside our planetary system. However, since then, more than 4,000 exoplanets have been found orbiting different stars. As illustrated by NASA, the universe could contain trillions of exoplanets. The earliest indications of something happening deep in space beyond our planetary system might be seen as extraterrestrial vegetation. The Galileo space probe, on its course to Jupiter, turned its instruments back toward Earth and saw a clear sign of the presence of plants, recognizing the vegetation red edge, a biosignature, a blend of red and infrared light reflected by plants. For example, a planet like Earth covered in a wild should have a strong signature, easily detectable. The JWST will measure the VRE of faraway Earth-like planets in the habitable zone around stars, which could provide significant indications of something occurring on a deeper level in the exoplanet's atmosphere. When light crosses a planet's star system, the JWST may have the ability to recognize it as it enters its atmosphere. The missing frequencies would then be seen through spectroscopy, as particles and molecules in the atmosphere absorb specific frequencies, creating a characteristic fingerprint that the JWST can recognize. This technique might be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with environments like our own, characterized by a mixture of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't ordinarily present, one might even detect intelligent life. For instance, chlorofluorocarbons, CFCs, made for use in refrigeration and cleaning products would likely be detectable to extraterrestrials analyzing Earth's atmosphere from a distant location. If the JWST detects CFCs in planetary atmospheres, it could indicate the presence of life. However, life on exoplanets likely will not resemble life on Earth in any way. Sometimes even ordinary living things like extremophiles, species that can survive in conditions where other living things would die, can seem alien. This group of life forms, generally microorganisms, can endure extreme conditions, such as temperatures up to 250 degrees Fahrenheit or acidic environments with pH levels below 3. Since planets like Earth are more likely to support life than those with extreme temperatures or acidic conditions, it might be wise to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is a yellow G-type star. These stars are more extraordinary and usually have shorter lifespans. However, in our universe, the probability of finding planets orbiting red dwarf stars, which are more common, cooler, and dimmer than our Sun, is higher. This long lifespan allows the development of life and evolution to produce complex creatures. Around 40 light-years from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It orbits a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets, located in the so-called habitable zone, could have liquid water on their surfaces. Despite its smaller and colder mass compared to our Sun, the TRAPPIST-1 star emits light similar to Earth's, making it suitable for its planet's nearby orbits. The most obvious opportunity to observe city lights outside the nearby planetary system is Proxima Centauri. A red dwarf star that is 4.25 light-years from the Sun. Proxima is much dimmer than the Sun, so a planet would need to be much closer to it than Earth is to the Sun to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable zone, a Goldilocks-like zone where the light force is ideal for melting water. Proxima B orbits Proxima Centauri. However, the fact that Proxima B is tidally locked makes it a potentially airless, dead planet. Since it orbits its red dwarf star only 4.6 million miles away, this close orbit exposes it to strong solar winds that could strip away its atmosphere. However, Proxima B gets enough light for temperatures and liquid water similar to those on Earth due to its proximity to the star. Proxima B is believed to be tidally locked, meaning it always shows the same side to the star, similar to how the Moon does relative to Earth. Proxima Centauri is about 18% the mass of the Sun and emits much less light than one might expect for a planet so close to the star, about 5% of the Sun's power. This could seem like a desolate, barren world, but liquid water could exist on Proxima B if the planet has an atmosphere to trap heat. Since the total energy reaching it from the Sun is only 65% of what Earth receives, the planet is not particularly conducive to life. It is likely tidally locked, meaning it constantly faces the same direction toward the star, creating a permanently hot side and a cold, dark side with extreme temperature variations. The planet also receives 4 times as much high-energy radiation as Earth does, including X-rays and ultraviolet light, due to its proximity to Proxima Centauri. Proxima B is also bombarded with high-energy particles during star flares. Unless it has a protective magnetic field like Earth's, conditions may not be ideal for life. Despite these harsh conditions, Proxima B might still be a more habitable world. Sadly, models suggest that the atmospheres of tidally locked planets may be prone to rapid degradation due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, their atmospheres are less likely to escape. Since we know nothing about Proxima B's volcanic activity or magnetic field strength, we can't even guess whether the planet has an atmosphere. However, since an atmosphere suggests the possibility of life, we are eager to know if Proxima B has one. It could have solar panels covering the day side to generate power to light and warm the night side, which would otherwise be too cold and dark for habitation. The discovery of Proxima B has triggered a race to determine whether it crosses its star's face as seen from Earth. These transits would allow scientists to determine the planet's size and mass, which would help them estimate its density and confirm its rocky composition, providing information on the materials used to form those rocks. During a transit, starlight could reveal the nature of the planet by passing through its atmosphere. However, the probability that the orbit will be aligned perfectly so that researchers can observe a transit is only 1.5%. The star's tendency to flare further complicates matters. Astronomer David Kipping of Columbia University says the star is unstable, as stellar heat makes a rocky planet absorb daylight and re-emit it as infrared light. However, rocky planets produce a distinct type of infrared radiation from stars like Proxima Centauri. The James Webb Space Telescope, which was specifically designed to observe infrared light, could potentially detect the infrared signature of Proxima B's atmosphere. Proxima B's infrared signature is important for identifying the planet's atmosphere. The infrared capability of the JWST, which surpasses that of the Hubble Space Telescope, could enable it to detect city lights on the night side of the planet, even if they are as faint as those currently used on Earth. The JWST could identify artificial lighting as long as it is restricted to a frequency band much smaller than the star's light. Proxima B's day side may be heavily covered with solar panels reflecting starlight, as Proxima B orbits its star constantly. The day and night sides are very different, with extreme temperature contrasts between them. The temperature difference between day and night depends on whether the planet is made entirely of exposed rock or whether air and water circulate heat. If there is no atmosphere, Proxima B's day side and night side temperatures will change more, as the day side will radiate all the energy it receives from Proxima Centauri as a black body. The night side would appear as a frozen wasteland. If the temperature difference between day and night is less pronounced, we can infer that future space exploration and the search for life beyond Earth hold great promise. The James Webb Space Telescope may be the key to finding extraterrestrial life in the universe. As the JWST searches for exoplanets, it will ultimately help shape our understanding of other worlds and our own. The search for extraterrestrial life has taken a grand step forward with the capabilities of the James Webb Space Telescope. While we have only just begun to scratch the surface of what it can teach us about planets in distant star systems, the discoveries made so far offer tantalizing glimpses of what could be out there. As we continue to observe exoplanets like Proxima B and others in the TRAPPIST-1 system, the potential to identify life, or at least signs that life once existed, grows. Even if these planets don't currently harbor life, their study will help us understand the conditions necessary for life to flourish. Each new discovery adds another piece to the puzzle of how life could arise in the universe. As we continue to look for biosignatures such as the vegetation red edge or atmospheric components like CFCs, researchers are also examining more subtle signs. Artificial lights, for instance, may not be the only sign of intelligent life. Variations in the planet's radiation or unusual patterns in its magnetic field could also signal more than just an indigenous ecosystem. The JWST's ability to detect and study these anomalies will provide an abundance of data about the potential for life beyond our solar system. The possibility of intelligent life existing somewhere in the universe remains one of humanity's greatest questions. The discovery of something as complex as city lights on a distant planet would be a game-changer in the search for extraterrestrial civilizations. Whether the evidence is incidental or indirect, it would prompt a reassessment of the uniqueness of life on Earth and the potential for other human civilizations to have developed in distant parts of the universe. Looking ahead, the JWST's role in uncovering the secrets of distant planets is invaluable. Its ability to observe exoplanets in more detail than ever before, especially in the infrared range, will allow us to explore their atmospheres, compositions, and even potential signs of life. Life on planets light-years away with its unmatched precision and responsiveness may only be a matter of time before the telescope detects something truly significant that confirms the presence of life elsewhere. As scientists continue to monitor planets like Proxima B and explore the potential for habitability, we are on the cusp of possibly rewriting the story of life in the universe. The age of space exploration and extraterrestrial discovery has only just begun, and the JWST will be at the forefront, guiding humanity toward new frontiers of knowledge and understanding. Ultimately, determining whether we find artificial lights, biosignatures, or other indications of life, the search for these discoveries enhances our understanding of the universe and our place within it. The quest for life beyond Earth is not just about finding others. It is about learning more about ourselves and the incredible complexity of the universe. Through the eyes of the James Webb Space Telescope, we may soon answer one of humanity's most profound questions. Are we truly alone in the universe? As scientists continue to explore the cosmos with the James Webb Space Telescope, JWST, they are poised to make even more groundbreaking discoveries. One of the most exciting aspects of this mission is the possibility of detecting life beyond Earth. While we are still far from conclusively proving the existence of extraterrestrial civilizations, every new observation brings us closer to answering the age-old question of whether we are alone in the universe. The JWST's infrared capabilities enable it to peer deeper into the universe than ever before, offering a glimpse into the atmospheres and conditions of distant exoplanets that could harbor life. In addition to studying potentially habitable planets like Proxima B and those in the TRAPPIST-1 system, the JWST is investigating a range of other intriguing celestial bodies. For example, it has begun observing exoplanets that exist in a variety of different environments, from those that orbit binary stars to those located in the dense, turbulent centers of galaxies. This wide range of planetary conditions could reveal more about the versatility of life and whether it can adapt to the various challenges presented by different cosmic environments. The search for intelligent life is particularly exciting, as subtle signs of advanced civilizations could be detected through technological signatures. The potential for observing artificial structures or energy usage, such as city lights, radio waves, or energy signatures indicative of advanced machinery, expands the possibilities for finding extraterrestrial intelligence. This extends the scope of the search beyond the mere presence of life to the existence of civilizations that might be capable of altering their environment in detectable ways. Furthermore, the JWST's observations are not only limited to planets in the habitable zone. Some researchers are also looking at planets that exist outside these zones, where life may survive under extreme conditions, much like extremophiles on Earth. Studying these planets could challenge our understanding of life and its potential to thrive in unexpected places. As the JWST continues its mission, it is certain that its discoveries will shape our understanding of the universe, offering insights into the nature of life, habitability, and the potential for future interstellar exploration.